Hi there, this is Prof. Johan from the Department of Chemical Engineering at the University of Pretoria. Welcome to my series on the Introduction to Chemical Engineering and Chemical Engineering Principles.
This video is a little bit of a bonus. I want to talk to you about Pascal's principle. Have you ever wondered how is it possible for you to use a hydraulic jack, press down on the lever and pick up the car on the other side? Me, small little arm, big car, push down on the lever and the car goes up. This is described as Pascal's principle, but how does it work? Now give me a second to make a little drawing. Here I have some sort of reservoir with two distinct pistons and the same fluid filling the whole system. The level on the two pistons will be exactly the same, and the pressure at both sides will be exactly the same. So let's now talk about the pressure at these 2 points, and let's call them point 1 and point 2. So P1 must be equal to P2. Why? Same fluid, same height, so the pressure of both sides are 0 gauge or atmospheric pressure absolute. We know that pressure is force over area. Let's say I've drawn this picture to scale. A1 is much smaller than A2. P1 equals to P2, P2 equals F2 over A2, and P1 equals F1 over A1. Now look at this. Because A1 is much smaller than A2, but F1 over A1 must still be equal to F2 over A2. This implies that F1 is much smaller than F2 to maintain the same pressure between the two sides. If I have my car standing on the end of my system with the large area, I can push down on the small area and keep the car in the air, because the area on my side is much smaller than the area on my car side. The force I need on my side is much smaller than the force exerted by the car on the car side. And this because the pressures must be the same at the same height for the fluid. I hope you found this one interesting. A second interesting example that works on Pascal's principle is the following. I have a tank filled with some fluid. This tank is next to a building where I'm standing on the 3rd floor balcony. I attach a straw to the top of this tank all the way up to the 3rd floor balcony, where I now go and throw water into the straw. So the water runs down the straw all the way, filling the straw from the bottom till it reaches the top. What will the pressure be at the bottom of this tank? Easy. The pressure at the bottom will be rho of the fluid times G times the height, with this height being the total height of the column of liquid. Now the interesting question becomes, what is the force at the bottom of the tank? And this is interesting. To calculate the force at the bottom, we know that P equals F over A. This implies that F equals PA, or equals to rho G HA. And this HA is not a volume, because the A is the area at the bottom of the tank, and the H is the total height of the column of liquid. So we see that the force is proportional to the height of the column of liquid, and the force is not proportional to the volume in the system. So irrespective of how small a volume is in my tube, the force at the bottom increases drastically, increases linearly with this increase in height. And we can quickly reach a point where this additional height causes such a pressure at the bottom of this tank that it will actually explode. I hope you enjoyed this and thank you for watching.